Hello, welcome to the last video of the dark matter part of this school. Today we're gonna change gears and start exploring a different candidate for dark matter, namely axions, which is quite different from what we have been seeing until now, which was basically the phenomenology of WIMPs, weakly interactive massive particles. So axions are quite different in many aspects. One of them is the mass they can have. The range of masses for axions can be as low as, can start as low as 10 to the minus 21 electron volts, for instance. And this bound is not coming from particle physics, but from the fact that you have already derived in the problems, having to do with the fact that you have to be able to accommodate the smallest galaxies in the Broglie wavelength of this species. So this is a huge macroscopic scale. So if they are so light, there are different consequences that we're going to explore, and also some kind of things that cannot happen for axions. For instance, axions of these low masses cannot be produced thermally. And the reason is that, remember that for a thermal relic to behave as a dark matter component, its mass should be bigger than the temperature, to be non-relativistic. But the temperature at which we know that there should be some dark matter around in the universe is as high as 1 eV. So that means that any thermal relic which behaves as dark matter at this time should have mass bigger or equal to 1 eV. And the axions, they can be as high as you want. There are theories for which you can try to crank up these numbers, but in principle the typical masses are much smaller. For instance, a preferred mass is around 10 to the minus 5 eV, the so-called QCD axion. And you can even go to ultralight dark matter or fuzzy dark matter scenarios. Where you explore a huge parameter space in masses. I also wrote here that we are not only talking about axions, but axion-like particles, the so-called ALPS, right? So if you heard about the word ALPS in this context, those are going to be particles which have some properties in common with axions. For instance, that they have, that they are represented by CP violating pseudoscalars, or some kind of motivations, but in principle axion-like particles are, there is more freedom to build theories than in the case of axions. So for the motivation of axions, and that's one of the most important points about axions, is that they are motivated not only by the dark matter problem, but also by the so-called strong CP problem. Which is the statement that in the standard model you can build an operator with this is the QCD gluon field strength. So it's the analogous of the field strength of photons, but for non-abelian cases. And this operator is a total derivative, which means that this operator doesn't contribute to Feynman diagrams, but it contributes to some observables through non-perturbative effects. If you want, the average the expectation value of this operator you compute it also taking into account non-perturbative effects is non-zero, and is going to contribute to some of the observables of the standard model, in particular to the electric dipole moment of the neutron. So if there is a constant in front of this operator, this constant can be measured. And the experimental result is that this constant is tiny. All right. So Is this a problem? Well, this is a dimensionless constant, so in principle, being large or small is not subject to the same problems as dimension full constants, like the Higgs mass. So there is no hierarchy problem here. It's just a mystery, in principle, why there is a number that could be anything and it's going to be much smaller than 1. Okay, so if it could be very high, it would be the same mystery. But some theorists have thought that this is a way to understand that there is some physics beyond the standard model, and this physics in this case is the axion. So this axion is axion. I let you find out why the name. It was a joke by one of the authors of the first papers on these ideas. The idea is that if you have an extra field in nature, and this field is a pseudo-Nambu-Goldstone boson, meaning that it comes from the symmetry breaking of some UV theory. So remember that you have some, for instance, in the standard case, you have a symmetry that is spontaneously broken, and you have some angle here, a field, right? Remember that the theories are invariant under a reparametrization of this field, and this is what is called a Goldstone boson. All right, and if you have such a field, it only couples through operators which have satisfied this symmetry, and this already tells you that the way you couple this guy to the standard model in the low energy case is going to include a coupling of the field to the same current we had before. And this is trivial because this is a total derivative. Well, it's not trivial to show that this is a total derivative, but if I tell you that this is a total derivative and you make a shift of this guy, you can easily see that what you find afterwards is you find that indeed you satisfy that this operator is invariant under this symmetry here. Okay. Why this is relevant? Well, because when you break the symmetry, you have to choose the value of the field somehow in this parameter space. So all of them are in principle the same, except for the fact that now in the Lagrangian there are two terms. One is this one is this one. All right, so let me write the integral. And the value of the field that you're going to choose is the one that minimizes, remember, the energy of the system. That's what the expectation values want to do. The same way that happens when you break symmetry with the Higgs, and it generates an expectation value. Here, again, the expectation value for phi is going to try to minimize the energy. So it's going to try to minimize here GG epsilon. Okay, you have to minimize this. Well, when do you minimize this? Well, you see easily when this goes to 0. Here I forgot to add, let me add it now, that since this is a 5-dimensional operator, when you normalize things canonically, you have to include a scale, FA. So I'm going to call FA for axion, and I'm going to put it here also before I forget. Okay. So when you take this into account, finally, the expectation value for phi wants to be equal to minus FA theta. All right. So in the early universe, if you want, when this symmetry was broken, phi was selected to this value. That's good. What happens now? Well, it happens that if this is true, then you see that the observed theta, which is the one that has to do with the sum of these two terms, is almost 0, or basically 0. So you can explain why the measured value of this quantity is so small. And that's why the axion has been claimed to be a solution to the strong CP problem. The most famous UV way to do it is the so-called Pechi-Quinn mechanism, okay, where you break a U1 symmetry. But there are all ways of, nowadays, a lot of different models where you can accommodate this mechanism. Right. This is a framework, and one of the things that you may be wondering is that, okay, yeah, that's great, but this symmetry does not allow a mass term in the Lagrangian. So this seems to be a problem to identify this as a dark matter candidate. This is true, but the same non-perturbative effects that I was telling you about can generate a non-trivial effect for the neutron dipole moment are also responsible for the fact that you may generate also a mass term for this guy through some non-trivial dynamics. All right, I'm not going to say more about this. Okay, it's a relatively complex quantum field theory calculation to show that indeed phi acquires a mass, okay, through some non-perturbative effects. And the good thing about this is that the mass, in this case, is going to be suppressed as compared to the UV scale of interest. Okay, so you have a theory which is UV complete with a very high scale. Since the mass is generated through these non-perturbative effects, so these suppressed effects, all right, then you can generate a hierarchy between the mass and the UV physics, and that's great because that allows you to have a candidate for dark matter with low mass, okay, with a mass which can be as low as, well, basically what you want, more or less, depending on the mechanism that you are putting forward. In the end, putting all together, this candidate is as simple as a free scalar plus some interactions which are typically suppressed, so we are not going to discuss them at all. All right, and for instance, you can go to some concrete mechanisms to for this mass, and this is a typical relation between the mass and the UV scale, and you see that there are several orders of magnitude between these two. Okay, and this is because, as I said, this is the way you generate the mass in this framework, right? But we are doing dark matter phenomenology. As I said, all these more quantum field theory explanations for now is just enough that you know that they are there, and if you want to explore them, well, there are several books. I particularly like the one by Weinberg on this, but this is up to you. Okay. So now let's see how this field behaves as a dark matter candidate, even if it has this very low mass. For this, we need to understand how is it possible that being so low in mass, it can still, behave as a cold distribution. So remember that means that you cannot produce it thermally. So we're gonna see how we can produce it in a different way. Non-thermal production of dark matter is a whole world. And I'm gonna only explain to you something called misalignment for the generation of this scalar field, and how does this behave as a dark matter component. Okay. All right, for the production, remember that we are exploring the situation where phi, this field, is made out of a expectation value, but this field will not be totally fixed by the expectation value. There will have some fluctuations on top of it. This may be quantum fluctuations, but also fluctuations driven by the fact that in the early universe there are high temperatures, so there may be other particles around that will make phi fluctuate around its mean value, right? So there may be thermal fluctuations or quantum fluctuations. Independently of the nature, the idea is that this value, phi will not be completely fixed as the universe is expanding. As the universe expands, then these fluctuations, okay, will be bigger or smaller. For instance, if they are connected to temperature, the temperature will decrease, so these fluctuations will be typically smaller, and at some point, okay, they will be kind of fixed, okay, and what we want to understand is how do they evolve with time, okay. So we're going to assume this situation in which there are fluctuations. At some point, these fluctuations drive your field to a time 0, let's say, a configuration 5 bar plus some perturbation on top of it, and from this time on, okay, the universe expands so fast that they are no longer important. These fluctuations are no longer important. The important thing is that the universe is expanding, okay, and this field from this time on is gonna behave according to the equations of motion coming from this Lagrangian and with these initial conditions. Okay, so let's see how this works. The initial conditions are given by this. Well, I didn't tell you what delta phi 0 is, right? This fluctuation. I'm going to tell you something more about this at the end. Let me now write for you the equations of motion for this Lagrangian. So you have to do the standard variation of the Lagrangian here to find the equations of motion. There is something tricky having to do with the fact that we are in an expanding universe, and in an expanding universe the kinetic part, okay, acquires also a time-dependent piece. This is a consequence of general relativity. If you have never heard about it, no worries. But the idea is that the kinetic energy also dilutes as the universe expands, all right? And it has to be parameterized by a factor of the growth factor. Remember the rate at which you are expanding, okay? And finally, this means that the equations of motion for this homogeneous configuration of the field are given by second time derivative of phi plus 3 a dot over a, first derivative of the field plus the mass squared delta phi equals 0. Remember that this we have called it already Hubble function or Hubble constant, depending on who you talk to. Right? Again, this has to do with the fact that the universe is expanding. Otherwise, you have here something close to a harmonic oscillator. Right? What do we want to know? Well, we want to know not this. Well, of course, we want to know the time evolution, but the most important piece is the energy density of the field. How does it evolve with time? Because to be reproducing the phenomenology of dark matter, it has to go and decrease as a to the cube, a to the minus 3, as the universe expands. Remember that radiation behaves as 1 over a to the 4, non-relativistic matter as 1 over a to the cube. Is it the case? Okay, that's the most important thing to check at this point to continue the calling this a dark matter candidate. For this, we need to know what rho, the energy density, is for a scalar field. And this is a classical exercise in field theory. And the final answer is given by this quantity. Again, kinetic energy, and here a potential energy. And remember that we are not taking into account inhomogeneities in the field. We only want to know what happens with fields which have, the derivative with respect to space equal to 0. Okay, homogeneous. And I think I said already, but the dot over the field means the time derivative of the field. Very good. Well, the only thing which is missing in this to solve this problem is to know what h is. So h is going to be given by the Friedman equation. Remember that the energy density determines how the universe expands, and once you have all this, you can solve this problem consistently. Let's take analytical approach and do this in the case that we can do it, solve it easily, where h is constant. So when the universe is expanding at a constant rate. Okay. When h is constant, you can go to this equation here and try to look for solutions of the form close to a harmonic oscillator. So we're gonna try to look for solutions of harmonic oscillator. Okay, so let's do with the plus. Yeah, then we will see if omega is imaginary or real from the solutions. Well, plugging this back in the equations, you find that omega satisfies this simple quadratic equation. All right, and you have already identified two limits. One is when this term dominates, one is when this term dominates. Let's first explore the case where h is much bigger than the mass, so when this term dominates, so forget about the mass. And in this case, what one finds is that, well, the solutions are given by omega equals 0 and, well, omega equals to minus 3h, right? So you see that this solution decays very fast with time, and this solution is a constant solution. So in this case, d phi behaves as constant, and meaning that once you plug it back in the equation for the energy density behaves as constant, so this cannot be a good dark matter candidate. So in this regime, it doesn't work. Let's go to the other regime. Okay, in this case, you have the opposite regime, and the solution is omega equals to minus 3h over 2 plus minus im. So you can check it that this is the solution in this limit, and that means that d phi is given by the initial condition again, E minus 3h over 2t, and here, well, there will be some oscillations coming from this guy, plus or minus, so you can put both together into a cosinus or sinus of mt and then some phase. Very good. So this is the time-dependent solution we were looking for. It decays with time, so it looks like we are in a better track now in this case. And indeed, when we compare it with A, so remember that we are in the situation where h is constant. So if this is constant, A behaves as an exponential. So when you can plug this back up here and realize that indeed d phi behaves as d phi 0, okay, e to the minus, sorry, not e, sorry, here, a to the minus 3/2 cos. And finally, with this time dependence, we can find what is the time dependence for rho. Okay, and you can easily plug this into the expression we had above here. In this case, we only care about the time dependence of the fluctuation, so you can just plug there. I mean, consider the part having to do with time dependence there, and it boils down to evaluating these two terms. Okay, if you are a bit careful, there will be also a linear term, but this linear term is not important for what I'm going to tell you now. So for the quadratic term, what you find is that this is going to be basically d phi 0 square, cosinus square, and 1 over a to the cube. So here we see what we were looking for, the fact that the energy density in this case decays as a dark matter component. Here there is a fluctuating function, so it fluctuates with frequency m. M is larger, this frequency is larger than the typical scale of the expansion of the universe, and that means that these fluctuations happen fast as the universe expands, and the important part of these fluctuations is the average of them, and the average of a cosinus is 1/2. I invite you to do this calculation. Sorry, of a cosinus square, because basically you have to do this integration. All right. Well, the phase doesn't matter. And yeah, of course, when t goes to a large t, when t is much longer than m. And finally, yeah, the only missing part here is the initial value of the field. So rho, if you want, the average rho is given by basically an initial component that is expanding, all right, and generating the same phenomenology as the collection of the particles that we had already in the WIMP paradigm. So the fact that rho, okay, the energy density behaves this way is telling us that this very different configuration, a field, okay, which is satisfying these field equations, okay, is also a good candidate for dark matter. There is something here which is non-trivial, the fact that, yeah, if the candidate is also dominating the expansion of the universe, all I told you is not consistent. Why? Because we were assuming that h is constant, but h is given by the Friedman equation, and if rho evolves with time, h also evolves with time. It cannot be constant. There's a way to show that also when the universe is dominated by this component rho of the axion field satisfying this equation, it indeed still behaves as a cold dark matter component. But for now, I think I prefer to go and explore other consequences of these models. Okay. All right. So yeah, here I forgot that this also has a mass on it, right? Okay, this comes from basically taking the time derivative twice, or simply by this term here. Okay, and now the question is, what fixes this initial rho? Okay, rho at time 0, okay, is going to be given by, okay. Well, again, this is fixed by the UV physics, and this is not the point of this module, of this lecture. The point of this lecture is to tell you that indeed there is a way to predict it, and in the Peachy Queen scenario, for instance, you can have the omega of this candidate today. Okay, this is, remember, this is rho phi over rho critical at values that are similar to the ones we have measured with the observations today, if the mass of the candidate is around 10 to the minus 5 eV. Okay, this is what I told you before, that it is natural, okay, to well, this is a kind of miracle, if you want, in the axion case, that it is natural to produce the relic abundance in a full theory the relic abundance that we see today, when the mass of this axion is around 10 to the minus 5 eV. Okay, so that's great. So as I said, now we're going to jump into a bit of phenomenology of axions, which is maybe more important for what you are, for your interest. So it was a crash course on why they are cosmologically relevant, and now how to detect axions. So there are two basic ways to try to detect axions. One of them is coming from the fact that the axions may be the dark matter, and they will have an abundance in the position of the sun. Remember that in the position of the sun, there is an energy density of dark matter given by this number, like 0.3 GeV per centimeter cube. That gave us the flux of dark matter in our detectors. For axions, their mass is so low, that we have to find other ways to detect them, not through recoil. Recoil is not a good idea. We have to find other ways to detect them. Indeed, for axions, we are gonna describe them even on the outskirts of our laboratories, not as particles interacting with the detector, but most as a field. The dark matter axion, sorry, interacting with our devices. And the reason why this is the case is because phi, okay, the axion field is a field with high occupation numbers and a certain degree of incoherence. And this is the characteristics. This characteristic allow us to consider the distribution of axions around us more as a field satisfying some classical field equations than as particles interacting with the detector. This is the same thing that happens with light. When you think about light around you in the room, you typically don't want to describe it as a collection of photons, but more as a field satisfying Maxwell's equations, because it satisfies these two conditions, that all states that you are interested in are highly occupied and that there is not coherence among them. Okay, this is, yeah. So in particular, this means that if we are interested in one operator, for instance this operator, of course you can also try to find this as a collection of particles, but the field description means that this guy here is going to have some expectation value, okay, that will have some dynamics, and it's going to modify whatever observations we are doing with this operator, as this is just as some time evolving configuration. So what is the evolution of the field in the solar environment? Well, I already told you what the energy density is, but what we want to know is really what phi is in the solar environment. Well, in the solar environment, phi has to satisfy the same equations as for cosmology. Here they are, okay, these ones. Now, if we are talking about time scales much smaller than the cosmological time scales, you can forget about this term here, and you see that what we are studying is nothing but a harmonic oscillator for this field. Also, we are talking about distances. Your lab scales are very small with respect to the typical wavelength of this classical field, so you can just forget about inhomogeneities and take into account that phi is simply going to be the solution of a harmonic oscillator with frequency omega and a certain initial condition. Oops, this is a different letter. What fixes phi 0 in this case is fixed by the fact that the energy density of the field, again, is what we wrote before, equals, if you plug this back here, m squared phi 0 squared over 2. Okay, you can check this. Yeah, and remember that we are averaging over the oscillations. And in this case, since we know rho, we know that phi 0 is given by, square root of rho twice square root of rho divided by m. And finally, you can plug this configuration into this operator. Where did this operator enter? Remember that this operator entered in the dipole moment of the neutron. And a way to look for it now, for this operator, is to measure this quantity and understand that it has to have some time dependent. So remember that now. Its value is going to be given by the theta angle, that is whatever it is, the phi over fa that tries to make this vanish, plus now some extra piece coming from the configuration around the solar system. That is going to be time dependent. So you look for these time oscillations in the observable, and the fact that you don't see it, okay, puts bound on the coupling. And also, since you are looking for a oscillation, you can make a spectral analysis, so it's even simpler if you want to make the analysis at different, for particular masses, okay? So you typically see that the sensitivity is mass dependent. For instance, if the oscillations are very fast, you're not going to see anything. If the oscillations are very slow, you don't see anything because they may average to 0. If they are very slow, it may be just a constant value that is also harder to find. Other ways to detect axions, you can try to find other operators that connect the axions to the standard model, and those should be operators satisfying the shift symmetry. Okay, and they should be also CP violating. The second natural operator that people look for is the gamma-gamma axion. Okay, that comes from this one. So here the axion, and here F nu, F alpha beta, epsilon mu nu alpha beta. So the same as in QCD, but now this one can be expressed easily in terms of the electric and magnetic field. Okay, and you can try to look now for this operator in different experiments. Phi, if it is the dark matter, you're going to keep oscillating, so you can try to look for instance, birefringent effects in light propagation, right? Because this is going to affect the different polarizations in different ways, right, of the light. Another way to look for it is directly trying to produce the axions, so not taking into account that phi oscillates, but really trying to generate a flux of them in your experiments or in the outskirts of your lab and detect them somewhere else. I mentioned this one, but because this is one of the main sources of constraints for axions, and this is coming from the fact that you see, when you have two photons, generate an axion. So photon, axion, and a source of this one requires energetic, of course, the biggest possible photons you can have, and there is also something called the Primakov effect, where indeed you have some atom, some some charges, so nucleus for instance, okay, you can more efficiently through a virtual photon generate this phi, this extra field. This is an effect which is quite efficient in the sun. So the idea now would be that the sun can be interpreted as a source of axions on top of those produced, on top of those that are there because they are dark matter, and you may try to find these axions in your laboratory. Well, how do you want to do it? Well, there are different ways. One of them is through a helioscope, as the famous cast helioscope. So what you want to do is now here put a magnetic field. So the axion now will propagate, find this magnetic field, and convert into a photon, right? Because of the same vertex that we had before. And you then try to look for these photons which will have a particular energy, in this case X-rays, okay, depending on the energy of the production and also on the magnetic field that you are using. Another way to look for axions is, as I said, now trying to produce them on Earth. And for this, what you do is you have a now strong source of photons going through a magnetic field. Then in this configuration, you will convert some of these photons into axions. Okay, so this, if you want, photons will turn into axions in the presence of a magnetic field. And now these axions will be able to propagate even if you put a wall here that blocks all the light. The axions will be able to propagate and eventually regenerate afterwards with the same process. Okay, so you go and you try to detect photons that have gone through this process of being first converted into axions. The axions travel for some time. Now you can compute, for instance, what is the probability of conversion of photons in the presence of a magnetic field. Okay, and this is similar, by the way, to the neutrino oscillations. If you are used to this phenomena, and you can, for instance, show that the probability of conversion in the presence of a magnetic field. Here it is. I give you this number. At a distance L, so this is the probability that at distance L you convert into axions. The most relevant quantity is this oscillation, delta oscillation, okay, which is given by two quantities. Yeah, and what I want to show you by this algebra is that this is proportional to the magnetic field, and also, quite importantly, to the ratio between the mass of the axion and the frequency of the light. So the first term here is the one precisely characterizing this ratio. Okay. And the second one, well, this you can basically put in numbers in. Well, these are typical numbers. There's some numbers I just put you here. And delta M, again, is important how strong the magnetic field is. You may say that, oh, why do you choose these weird numbers? Like 1 Gauss. Sometimes you can do better than 1 Gauss. Also these photons which are in the lab 10 to the 19 eV, so seems crazy. Yeah, I put these numbers because these are numbers relevant for another process. Okay, 5 parsec -1. Okay, so those are numbers. Well, you can plug now whatever your values are, but those numbers are also relevant for the following process, that if you have photons in the early universe and they are coming to you, they will also, some of them, turn into axions if there are magnetic fields, let's say in the galaxy. Okay, and this is a different way to also look for axions. So we have direct detection by the sun, direct production by the sun, direct production by you and detection by you. And again, you can put these numbers in. And the important point about this one is that the amplitude and the oscillations have to do with the ratio between the mass and the frequency and the strength of the magnetic field, as you would expect. But also you can look for it as, you have a source of light far away from you, intense source of light like a quasar, and you can try to look for conversion of this light into dimming, for instance, of this light at certain frequencies, right, as it reaches your telescopes on Earth. Indeed, for the action searches, astroparticle physics and astrophysics are one of the most stringent ways to look for them. Other places are indeed, and I mention this because you will see them in all the plots about actions, are the plasmas in stars. So you have actions on top of the standard model particles in a star. Photons, when they interact with each other in the plasma, may decay into actions. Okay, for this process, as we did before, you need some extra. You need this to happen in an environment. Okay, for this to be possible. And it turns out that in the plasmas, okay, you can have this pre-Markov effect. You can have electrons. You can have positrons, and eventually, because you are able to produce actions so efficiently, these actions will leave the star and if the coupling is such that this happens efficiently, you will cool the stars so fast that you won't be able to explain the evolution of stars that is very well constrained experimentally with observations. Okay, so cooling of stars. Putting all together, the bounds that you can put for cooling of stars are of the order of 10 to the minus 10, over GeV. So this is a typical constraint for the couplings, and this is true for masses below MeV. Any particle that is coupled in this way at these masses, which are basically taking all the parameter space that we are interested in, cannot be coupled to photons stronger than this way. The reason why we go to MeV is that the MeV is the typical temperature of the stars that we are interested in. So if actions would have masses above MeV, you wouldn't be able to produce them anyway in the stars. And this finishes our lesson on actions. Before concluding, I just realized I didn't comment on the units that I use here for the quantities appearing in the probability of photons to decay into actions in the presence of a magnetic field B. So these units are parsec to the -1 because the parsec is the typical scale for this process for astrophysical conversion. Okay, remember that 1 parsec is around 3 light years. And this is it for this lesson and for the whole module. This lesson was dealing with axion motivation, something about production, something about why they are dark matter candidates, and finally, something about how to detect them. Right? Of course, this is a whole universe, axion phenomenology, and I hope that you can find some reviews in my notes that will allow you to go deeper into this topic. The same is true for the rest of the dark matter things I have been teaching. I'm trying to give you a flavor of different aspects, but of course I cannot give you a full review. Go into the literature that I mentioned in the notes, and hopefully you will be able to find everything that you want. Unfortunately, I couldn't say anything about indirect detection, so I decided instead of doing that to say something a bit more about axion detection, to give you a more modern idea of ways in which people are looking for dark matter nowadays. But of course, indirect detection is a very, very important topic that again you can find in the other reviews. And that's it. It has been a pleasure and also a challenge to record these videos. It's really tough to try to be precise and record the lessons in these conditions. But, well, I hope that you enjoy them and that we will be able to meet soon in real life and discuss about dark matter or any other interesting physics. So thank you very much.